The JUTEC Bending System 5000 begins with the operator inserting a tube and selecting a preset program. The plug-in bending tools are quickly installed to match the tube size. The compact drive unit and freestanding bending head enable both right and left bending, especially for tight radii and complex geometries. During bending, the mandrel retracts automatically once the desired angle is reached. Fast hydraulic motion helps reduce idle time, supporting efficient series production. The hot bending process begins by locally heating the steel tube with an induction coil until it becomes red hot and flexible. Water is sprayed during bending to fix the shape and prevent warping. The tube is then clamped and bent around a fixed die. After bending, it is cut, inspected for dimensions, heat-treated, and undergoes destructive testing, magnetic particle testing, and ultrasonic testing. Finally, the tube ends are beveled to complete the process. The shown machine is an outdated model, no longer available, replaced by an improved version. This older mandrel bending machine uses various tools for precise tube bending. The clamping unit firmly holds the pipe in place. A thrust bearing supports the bending motion counter rollers are used for thick-walled tubes, while slide rails are used for thin-walled ones. Bending mandrels reduce ovality and prevent wrinkles on the tube surface. The bending tool determines the bending radius. For example, a 42 mm tube may have an 84 mm radius. Rigid mandrels are applied for thicker pipes with large radii. For thin-walled tubes and tight curves, ball mandrels with movable balls are used to support deeper into the bend. When wrinkles occur, a wiper die may be added to prevent them, especially for unannealed tubes. This setup ensures accurate, smooth bends across various tube types. The DN450 ball valve body is securely clamped onto the lathe by the operator. Once properly fixed, the lathe is activated, and the turning process begins. The machine precisely removes excess material, shaping the valve body to meet specified dimensions and ensuring a smooth surface finish. The cruise ship MSC Magnifica entered dry dock, where dock blocks supported her hull. Crews replaced 40 tons of steel, painted over 6,000 square meters, and serviced lifeboats and davits. Old rudders were removed and modified stocks, installed with cooled bearings. Stabilizers and thrusters were repaired, propellers polished, and anti-fouling applied before undocking. The longitudinal submerged arc welding process involves joining the edges of a formed steel pipe using arc welding beneath a blanket of granular flux. First, the pipe is positioned and aligned precisely. Then, an electric arc is generated between a continuously fed wire electrode and the seam, which melts the edges and filler wire. The molten weld pool is protected by the flux layer, which prevents contamination and stabilizes the arc. Welding is done both inside and outside the pipe, using automatic welding heads. This method produces deep, uniform welds with excellent mechanical properties and minimal spatter, ensuring strong, durable joints. The seamless steel pipe manufacturing process begins with heating steel billets, followed by hot rolling, punching, and rolling. The pipes are then sized, cooled, straightened, and cut. After heat treatment, including hardening and tempering, the pipes undergo straightening, ultrasonic and hydraulic tests, final inspection, marking, and packaging. The cold forming process begins as galvanized strip with a thickness of 0.3 to 0.6 millimeters is fed into the machine through the uncoiler. The material passes through the feeding section and enters approximately 12 forming stations where it is gradually shaped by rollers. The roll forming process is powered by a gear transmission system, allowing a consistent forming speed of 30 meters per minute. After forming, the shaped profile is cut to length using a hydraulic cutting system, ensuring precise and clean cuts. The cut products are then transferred to the runout table for collection. Finally, the formed steel profiles are packed for delivery. This process provides high efficiency and accuracy in producing cold-formed steel sections. The seamless steel pipe manufacturing process starts with heated billets from a converter, which are fed into an annular furnace. The red-hot billets undergo piercing to form hollow tubes. These are then processed through the pipe mill and sizing mill for accurate dimensions. After cooling, the pipes are sawn, straightened, and visually inspected. Non-destructive testing ensures quality. Finally, the pipes are marked and packed for shipment. The manufacturing process of 100 NB mild steel tubes begins with feeding a coil of flat metal strip into a continuous coil accumulator. The strip is then uncoiled and guided into the Parth 115 TMERW tube mill. In the forming section, the strip passes through several rolls that gradually bend it into a round tube. Once formed, the edges are welded together using electric resistance welding, where high-frequency current heats the edges to create a strong, seamless joint without filler metal. The welded tube then undergoes sizing to achieve the required diameter and shape. An online non-destructive testing system inspects the weld integrity. Finally, the finished tube is cut to length and prepared for further processing or packaging. The slitted coil is uncoiled and fed into the forming section via the entry section. The strip is joined and accumulated for continuous operation. The pipe is shaped into a round form by rollers, then longitudinally welded using high-frequency induction. After bead removal and cooling, it is sized, cut, and collected. The production of square aluminum tubes begins with selecting high-quality aluminum alloys such as 6061, 6063, or 7075. The raw material is melted in a furnace and cast into billets. These billets are then heated and extruded through a square-shaped die using an extrusion press. After extrusion, the tubes are cooled, straightened, and cut to the required length, typically up to 6,000 millimeters. Depending on customer requirements, various tempers like H112 or T6 may be applied through controlled heat treatment. The tubes are then subjected to surface treatments such as anodizing or polishing to improve corrosion resistance and appearance. A final inspection ensures dimensional accuracy and surface quality. The finished products are packaged using waterproof tape and strapping to prevent damage during transportation. Finally, they are shipped from ports such as Shanghai or Qingdao to international markets including Europe, Southeast Asia, and North America. The hot elbow making machine uses hydraulic propulsion and induction heating to form elbows ranging from 1D to 2.5D. The raw pipe is clamped, aligned, and heated, then pushed into a heated mold to form the bend. Electromagnetic valves allow dual control for efficient and safe operation. The DW75CNC8A3S automatic servo pipe bending machine uses a high-efficiency gear servo system to bend aluminum tubes with precision, plus or minus 0.05 degrees to 0.1 degrees. Tubes are clamped and pushed into the bending dies. Each bend can be programmed with specific compensation values, speeds, and die clearances. The control system automatically adjusts for material springback and minimizes pipe interference. An optional automatic oil spray system reduces elbow friction. Real-time 3D visualization and XYZ-YBC coordinate conversion enhance operation. The system also supports manual or automatic memory functions to prevent collision and ensure smooth production. Round tubes are first fed into the loading system, where they are aligned and automatically loaded onto the machine. The CNC program controls the positioning and rotation of each tube to ensure precise alignment with the laser head. A fiber laser beam is then directed onto the surface, cutting through the material with exceptional speed and accuracy. The system uses different assist gases, air, oxygen, or nitrogen depending on the tube material, such as iron or stainless steel. Complex cuts, including holes and slots, are executed seamlessly in one continuous operation. After cutting, the finished parts are automatically unloaded onto a collection tray. Throughout the process, the machine maintains high precision and minimal material deformation, enabling fast and repeatable production without tool changes. The operator inserts the steel bar into the designated slot of the GW40 per gigawatt 50 rebar bending machine. After aligning it with the adjustable stopper, the machine is activated. The central disc rotates, pushing the bar against the fixed pin to bend it to the desired angle. The process is quick and precise, with minimal noise. Upon completion, the bent rebar is removed manually, ready for use in construction. The flat bar 200 by 100 millimeters is first positioned into the MAHACHD section bending machine in a horizontal orientation. The machine secures the bar between 3 driven rolls, with hydraulic guide rolls ensuring precise alignment. Using planetary movement of the bottom rolls, the machine begins to apply controlled pressure, gradually bending the flat bar along the hard way. The bending process is monitored with a programmable digital readout to ensure accuracy. As the bar advances, it forms a smooth arc with minimal deformation. The heavy-duty machine allows tight radius bending, completing the process efficiently without the need for test bends. The stainless steel exhaust pipe is first positioned into the CNC pipe bending machine. The rotary draw bending technique is applied, with a clamp die securing the pipe and a pressure die supporting it during bending. As the bending arm rotates, the pipe is drawn around a fixed bend die to achieve smooth, accurate curves. The CNC system precisely controls the bending angle and radius, ensuring consistent results. After each bend, the pipe is repositioned automatically for the next curve, allowing complex exhaust shapes to be formed efficiently and with high repeatability. The disassembly of the 3-inch 600 trunnion mounted ball valve begins by removing the body adapter, All adapter bolts are unfastened using a wrench, and the adapter is gently separated from the body with a flathead tool to avoid damaging the ball. Once opened, the seat ring inside the adapter is pushed out from the backside. The seat includes an O-ring, graphite fire-safe seal, and springs. Next, the trunnion is removed by unbolting the 4 trunnion bolts. A flathead tool is used to wedge and pull the trunnion from the body. The trunnion includes a gasket, secondary and primary O-rings, and supports ball rotation. Then, with the valve in the open position, the ball is pulled out through the stem slot. The mounting plate, secured by 4 bolts, is removed, followed by detaching the stem bushing by unscrewing its 2 Allen bolts. The stem is pushed out, showing its O-rings, bushing, gasket, and anti-static device. Finally, the body seat ring is pushed out. All components body, adapter, ball, seats, trunnion, stem, bushings, and mounting plate are laid out, completing the disassembly. The assembly process begins by constructing the legs using basic tools. A T is placed on each smaller pipe to act as a stopper inside the larger telescopic pipe, allowing height adjustment. Plastic pipe caps are pounded into the ends of the smaller legs. Next, a crossbar is installed to connect both sets of legs. Once the frame is complete, it is positioned and attached to the desktop. The crossbar is then adjusted to the desired position. Optionally, a keyboard tray can be connected. The desk is lifted, and the legs are adjusted to the preferred sitting or standing height. Finally, set screws on each leg are tightened to lock the height in place, and the desk is leveled. Disassemble valve. Clean interior with solvent or wire brush. Sandblast exterior, replace seats, gaskets, packing, reassemble, and hydrotest. Ball valve components are precisely machined using CNC lathes and milling machines. The ball is polished for smooth operation. Valve seats are manufactured and assembled with tight tolerances. Body parts are drilled and threaded. Final assembly ensures proper alignment before pressure testing for performance validation. Steel plates are cut and welded to form blocks. Blocks are assembled into ship sections using cranes. Outfitting, including piping and machinery installation, is performed. The hull is launched, followed by painting, final outfitting, and sea trials. The shipbuilding process begins with the cutting and welding of steel plates into panels, which are then assembled into hull blocks. These blocks are pre-assembled with structural reinforcement, piping, and basic assembly. Each completed section is transported to the slipway by a large crane. In the assembly area, a large gantry crane lifts and aligns the blocks with high precision, where workers weld them together to form the hull structure. As the block erection process proceeds, the ship's internal compartments, such as the engine room, fuel tanks, and living areas, are formed. The deck structure and side hull blocks are lifted and integrated. Assembly continues in parallel, including the installation of ventilation systems, piping, electrical cables, and machinery. Large components such as the funnel and bridge are lifted and installed on the upper decks. At the stern, the propeller shaft, rudder, and rudder are installed. Workers also install the anchor and winch at the bow. After the whole assembly is complete, the vessel is painted and waterproofed. Final assembly and systems integration are carried out before the dry dock is submerged. The vessel is launched, followed by sea trials to verify performance and safety standards before handover to the customer.
Lay it on, like so, and bring it out. You don't want to paint back and forth like latex. You want to go straight out like so. Probably should have taped that off.
The teak railings on the yacht were thoroughly sanded to 150 grit for a smooth surface before applying the acetyl finish. The first coat was applied using a brush dipped lightly in the varnish, laying the product down in smooth, straight strokes rather than back and forth painting. Application started at one end of the wood, with the brush gliding in a single direction to allow even absorption. The product began to seep into the grain of the teak almost immediately. After applying a few feet of coating, the surface was tipped off using a dry brush to help the finish settle evenly and soak into the wood.
That's what we're looking for. Start with your puddle here and then move your way through it, going in one direction at all times. Like so. Get a nice coat down on it. Let's say 3-4 feet, and tip it off with a dry brush. Once your brush you start hearing your brush, then you want to tip it off, like so. And that'll let it
the process continued along the entire rail, always starting from where the last section ended. When the brush started making noise, indicating it was too dry, it was reloaded with product to maintain smooth application. After the first coat, the surface was allowed to dry. Once the product began to puddle on the second coat, excess finish was wiped off with a clean cotton towel. This step ensured the proper buildup of the finish without oversaturation. The second coat further enhanced the color and texture of the teak, setting the surface up for a potential gloss top coat after full curing.
Now this is just the first coat. We're probably going to need 2 or 3 coats until this puddles. Once this puddles, then we're just going to wipe it off with a clean towel, cotton towel, and then we're going to be ready for a gloss.
In August 2018, construction began on the large steel artwork Tango, designed by artist Fons Schaubers at Smoleniers Constructie am Plaatwerk BV in Nederweert. Due to its planned height of 10 meters, the sculpture was fabricated lying on its side to accommodate the workshop's ceiling height and technical constraints. 3 experienced workers handled the building, welding, and ongoing consultations, with a scheduled construction period of 12 weeks. Midway through, representatives from the municipality, province, and sponsors visited the factory to observe the progress. The assembly continued steadily according to plan. In early November, a critical step came when the sculpture had to be moved outside. Because the workshop's rolling door sagged slightly in the middle, the structure was lifted slightly to pass through. A temporary cutout in the sheet metal allowed it to rotate precisely through the doorway. Afterward, this cutout was filled and the surface ground smooth. For transport, the sculpture's protruding tip was fabricated separately to reduce height, but its fit was tested in the factory. The main structure was then painted in its final color. Meanwhile, in Venlo, the foundation and conduit for the lighting system were prepared. The first transport stage moved the sculpture 500 meters from the factory to the canal quay in Nederweert. Steel plates were laid and obstacles temporarily removed along the route. From there, it was shipped by barge to Belveld, a 6-hour journey, and moored overnight after the first lock. At dawn, the final leg brought it to the Maas Boulevard in Venlo. Large crane, supported by 2 additional cranes, lifted the sculpture's main section onto the quay. The separate tip was positioned and welded in place, with all dimensions fitting to the millimeter. The support frame used for construction and transport was then removed. The sculpture was carefully tilted into its final upright position and lowered onto its foundation. Some minor adjustments were required due to the inclined setup path. In the following days, surface imperfections were corrected and final paintwork applied. On November 30, 2018, over 5 years after its conception, the Tango sculpture was officially presented at its prominent location along the Maas in Venlo. The NAVIJETC300E2 is a versatile, general-purpose electric high-pressure cleaning machine designed to deliver powerful cleaning performance in both industrial and marine environments. Operating with cold water, it can handle feed water temperatures of up to 60 degrees Celsius, making it suitable for a wide range of cleaning tasks where hot water is not required. Built with a robust stainless steel frame and a matching stainless steel cover, the Navijet offers excellent corrosion resistance and durability, even in harsh working conditions. Its design incorporates 4 sturdy wheels, allowing operators to easily move the machine across different surfaces, ensuring maximum mobility and convenience during operation. At the heart of the system is a high-performance pump driven by a low RPM motor. This motor configuration not only enhances the machine's efficiency, but also extends its service life by reducing mechanical stress and wear. The result is a cleaning unit that provides reliable long-term performance with minimal maintenance requirements. The machine electric operation ensures consistent pressure delivery, making it effective for removing dirt, grease, salt, and other stubborn residues from a variety of surfaces. Its sturdy construction, combined with thoughtful engineering, makes it a dependable choice for ship maintenance, dock cleaning, industrial facility upkeep, and other demanding applications. In summary, the Navijet combines strength, durability, and ease of use in a compact, mobile package. With its stainless steel build, powerful yet efficient pump system, and user-friendly handling, it stands out as a high-quality solution for professionals seeking reliable, high-pressure cleaning performance. Marine abrasive blasting is a cost-effective and eco-friendly method for cleaning and preparing ship and boat surfaces. This process effectively removes rust, corrosion, oil, grease, and other contaminants, as well as marine growth such as algae and barnacles. It also strips away old paint and coatings, ensuring a clean, smooth surface that is ideal for repainting or recoating. Using high-pressure abrasive materials, the blasting process reaches even hard-to-access areas, restoring the vessel's exterior to optimal condition. Suitable for ships and boats of all sizes, marine abrasive blasting not only enhances appearance but also extends the vessel's lifespan by preventing further damage. Additionally, it ensures better adhesion of new protective coatings, improving durability and performance in harsh marine environments while maintaining environmental responsibility through controlled blasting techniques.